coming back for the last. Yes, thanks for remembering that. So thanks for coming back for the final talk of the workshop. So our last speaker is Julie Tourniaire, who's going to talk about spatial dynamics of a population in a heterogeneous environment. So thanks very much, Julie.
Thank you. I also want to thank all the organizers for having me in this conference. So I'm going to talk in this presentation about the propagation speed of a population colonizing heterogeneous environments. So it is based on a joint work with my two PhD supervisors, who are Pascal Maya and Gaël Raoul. I'd like to start with a simple example to put this problem into context and to illustrate the results. So consider a population that colonizes a linear habitat constituted of an alternation of favorable and unfavorable patches. So this can describe, for instance, fields divided by roads. And this can be modeled by a function, a growth rate function, that is space dependent, taking large values in favorable patches and much lower ones in unfavorable patches. So more generally, if we want to describe environments varying with time, we can consider time-space dependent growth rates. And in this work, we are interested in slowly varying environments. So we introduce a small parameter epsilon, that is the scale of heterogeneity of the environment. And instead of considering a function r of tx, we'll consider a function r of epsilon t, epsilon x. And the question is, what is the asymptotic behavior of the population when epsilon tends to 0? Okay, so the first approach to solve this problem is the large population asymptotics, which has been widely documented in PD theory. So we start with an individual-based model with local density K. So an individual-based model means a model in which we describe the reproduction and the displacements of each particle. So for instance, we can consider a particle system evolving in generations on discrete sites. And in this case, the system can be described by its configuration, where nk of I denotes the number of particles living on the site xi after the kth generation. And saying that the local density of the population is capital K means that on a site, when the population reach the saturation state, the population size is approximately capital K. So the large population asymptotics consists in taking the limit k tend to infinity in this model. So we weight all the individuals by 1 over k, and we consider the limit as k tends to infinity. So if we also let delta t and delta x tend to 0, we get that u nk over k converges to a certain density, and we will be interested in the densities that are solutions of Fisher KBP type of equation. What the reaction term is our growth rate with the scaling parameter times a function of u satisfying the KPP conditions. So you probably know that in homogeneous settings, there exists traveling wave solutions decreasing from 1 to 0. And in this case, we define the position of the invasion front as the rightmost position where the solution is larger than 1/2. So in this case, we define the invasion front similarly, and we denote it by x epsilon. So I recall that we are interested in the behavior of x epsilon as epsilon tends to 0. So from this point of view, we introduce an hyperbolic scaling by dividing the time and the space variables by epsilon. And we get a new function u epsilon that is a solution of this new equation. So we remark that in this equation, the diffusion term tends to 0 and the reaction term blows up when epsilon tends to 0. So as a result, the log density, V epsilon, converges to the viscosity solution V of an Hamilton-Jacobi equation. And that the position of the invasion front, x epsilon, also converges to a function that corresponds to the rightmost position where this log density is equal to 0. So this method has been widely employed so far to deal with different kinds of heterogeneous environments, so slowly oscillating ones, random medias, and so on. But one first drawback of this method is that it hardly provides an explicit propagation speed, except in very specific cases. So a second drawback is the possible qualitative disagreement between the probabilistic model and its large population asymptotics, which is a deterministic model. And this is due to the fact that there is no extinction in Fisher KPP equations. So even if the initial condition U0 is compactly supported, you get that the density U solution to the FKPP equation is positive for all time t. So it means that exponentially small populations are sent to plus infinity by diffusion. And if this small population reaches a patch that is favorable, in which it can expand quickly, then you can observe a jump in the position of the invasion front. So this is illustrated in this figure. So the blue line is the density, the orange dots, the position of the invasion front, the gray patches are the favorable patches, and the white ones, the unfavorable patches. So you see that the orange dot is stuck for Y, and then it jumps to the following gray patch. Okay, so some corrections was suggested from the PD point of view. For instance, adding a negative square root with a sail to cut the tail. But the question is, what is the biological interpretation of this term? So for biological concerns, we suggested another solution. That is, we first let epsilon tend to 0 in the individual base model, and then we consider large populations. So the question is, what is the speed of propagation in this case? And do the two limits commute? And you can guess that the answer is no. So here is the model that we considered. It is an interacting particle system evolving in generations and on discrete sites. So we denote by delta t and delta x the time and the space step. And again, we have the three parameters, the local density capital K. It can be seen at the strength of the competition in the particle system. So the larger K, the weaker the competition. Then you have epsilon, the scale of the heterogeneity of the environment, and the growth rate R that takes only positive values. So again, we denote by nk the configuration of the system at time tk. And in this case, the position of the invasion front will be the position of the rightmost particle at time t. So there is no tail, there is no particle after xk star. So then the model evolves as follows. So at each generation, the population on each site is renewed, and the population on a site is replaced by a random number of children governed by a certain reproduction law that depends on the growth rates, on the number of parents on the site, and on the strength of the competition. So once the population is renewed on each site, all the particles migrate independently according to mu, that is discretized Gaussian distribution. So what we assume on the law nu or nk, essentially it is the law of a truncated sum. So the sum is the sum over all the parents of the number of children. If we assume that they reproduce independently according to a law nu r that depends only on the growth rate r. And we assume that this law nu r is increasing in the sense of stochastic domination with respect to r. So the larger r, the larger the offspring. Then we assume that the expectation of y1 is 1 plus r delta t, and that each parent has at least one child. And then we truncate the total number of children to k to model the effect of competition. So here is an example of such an evolution. So we start with a configuration nk with nki individuals on site. We choose mu r, that is the reproduction law. Each parent duplicates with probability r delta t and does not duplicate with probability 1 minus r delta t. So it satisfies all the previous assumptions. So each parent gives birth independently. Then we apply the competition step. We kill randomly some newborns to get at most k individuals on each site. And then all the individuals migrate. So for this model, we got the following results. So if we assume that the system starts with its rightmost particle at 0, and if we consider a time capital T, we get that if the time and space steps are small enough, and if the local density is large enough but fixed, then the rescaled position of the rightmost particle converges to a solution of an ODE. ODE that is given by x prime equals to square root of 2r of x. Okay. So remark that the ODE evolves on the time scale of order 1, while the rescaled position on the time scale of order 1 over epsilon. Okay, so now let me show some simulations to illustrate these two double limits. So again, we consider this simple reproduction law for a function r that is 1 periodic and 1, 0, 1 that is a step function, taking high values on 0, 1 half, and low values on 1 half 1. And for this choice of reproduction law and growth rate, we plot the rescale position of the rightmost particle in the system for one simulation of the process, the position of the invasion front for the limit PDE. So it is not exactly the limit PDE, but it is a PDE whose behavior, whose propagation speed at order 1 is the same than the limit PDE of the process. And we plot the solution of the ODE from the theorem. So this is the position of the invasion front in the PDE. We can observe 2 jumps. This is the simulation, one simulation of the process, and the solution of the ODE. So if we fix epsilon, and if we let k increase, we see that the green line converges to the blue one. Now, if we fix k and we let epsilon decrease to 0, we see that the green line converges to the ODE, the graph of the ODE. So the main idea of the proof is to establish a coupling lemma to locally compare the process with branching random walks, because for branching random walks, we know the speed of the rightmost particle. And we can establish such a lemma because the system is monotone with respect to R and also with respect to K in the sense of stochastic dominance. So we compare our process, our system with some branching random walks on different time intervals. We get several estimates with linear speeds, constant linear speeds, and this allows to recognize the Euler scheme of the ODE from the theory. Okay. So the conclusion of this presentation is that if we consider the individual based model that are introduced in this presentation, and if you let first k tend to plus infinity and then epsilon tend to 0, you get that the spreading speed converges to the speed of invasion of the PDE. And if you invert the 2 limits and you first let epsilon tend to 0 in the individual base model and then you let k tend to plus infinity, you get that the position of the rightmost particle converges to the solution of the ODE. And what is important is that the ODE, the propagation speed of this, in this case, is smaller than the one in the large population asymptotics. It can be equal, but it can also be strictly smaller. So that's all. Thank you for your attention.
Thank you very much. So does anyone have questions? I have a naive question if no one immediately has a question. So maybe I'll start. So I think you said that you don't allow your particles to have 0 offspring, is that right?
Yes.
And how important is that assumption, do you think?
it's important to establish a lower bound on the propagation speed. But if you don't assume that this condition, the upper bound, I mean, the fact that the escape position is smaller than the ODE still holds.
Okay, so you can still show in that case that that the limits don't commute, I guess.
Yes, because it's lower than the PD.
Yep. Okay. Yes. So are there any more questions? So if not, then shall we unmute ourselves and thank Julie again for her talk, and also all the rest of the speakers this afternoon.
So this was the last talk of this branching structure meeting. So I'd like to thank again all the speakers and all the participants who made this event a success. And I'd like also to remind you that tomorrow and Friday we are running 2 days, which are the nuclear days on the neutron transport equation, which will be, I think, at the same time. Is that correct, Pascal?
They're starting at 9 a.m.
Yep.
Oh, it's 7 a.m. So sorry.
They're much more hardcore than us.